Yeah, good morning friends. Today we will going to talk about the phase lock loop. Now phase lock loop, it can be used to track the phase and frequency of the carrier component of an incoming signal. Therefore, it is a useful device for synchronous demodulation of AM signal with the suppressed carrier or with a little carrier. Now it can also be used for the demodulation of angle modulated signals, especially under the low SNR conditions. So for this reason, the phase lock loop, nothing but the PLL, is used in such applications such as space vehicle to earth data links, where there is a premium on transmitter weight or where the loss angle, the transmission path is very large. And most recently in commercial FM receivers, the PLL is used. Therefore, in this particular unit of FM demodulation, we are already having the method to learn about FM demodulation by using phase lock loop. Now first, let's understand the little bit about the phase lock loop, and then later on we will going to talk how the PLL is used for FM demodulation. Now here in this slide, here you are observing the block diagram of the phase lock loop, which basically having the three components. The first component, which is the voltage control oscillator. The second component, which is the multiplier, and the third component, which is the loop filter H of S. Now the operation of the PLL is very much similar to the feedback system, what we generally used to discuss in control system engineering. Now if we just see this particular block diagram of PLL, so you probably observe this particular block diagram as a closed loop control system. Now we know in typical feedback system, the signal feedback tends to follow the input signal. If the signal feedback is not equal to the input signal, the difference, which we generally known as error in control system, will change the signal feedback until it is close to the input signal, right, which we generally observe here. Now a PLL operates on the similar principle, except that the quality of feedback and compare is not the amplitude but the phase. Now VCO adjusts its own frequency until it is equal to that of the input sinusoid. Now the frequency and the phase of the two signals are in synchronism, or we may say they are in synchronous, except for the possible difference of the constant phases. Now this is the condition that what we are considering at this moment. Now let's see a little bit information about the VCO into the next slide. Yeah, so let's say, so if you're talking about the VCO, right, so which is an oscillator whose frequency can be controlled by an external voltage, and that's why it is called a voltage control oscillator. Now in VCO, the oscillation frequency varies linearly with the input voltage. Now if a VCO input voltage is, let's say we consider here E0 E naught of t. Okay, so like it's E naught of t and its output is the sinusoid of frequency, which is the, we may say, omega, or we may consider as omega of t, which is given, okay, here as omega c is equal to omega c plus c E naught of t. Now where c is the constant of this particular VCO and omega c is the free running frequency of the VCO. Now free running frequency is nothing but the frequency of the VCO when E naught of t is equal to 0. The multiplier output is further low pass filter by the loop filter, which we can observe into the block diagram of the phase lock loop. Okay, so this multiplier output is further low pass filter by the loop filter and then applied to the input of the VCO. Now this voltage changes the frequency of the oscillator and keeps the loop lock, and that's why the name what you can see for this particular operation, that is as the phase lock loop. Now let's further understand how the PLL basically going to work. Now if you just check the if you concentrate on the block diagram here, what we are considering input to the PLL as input to the PLL as A sine omega ct plus theta I, and let the output to be a sinusoid, which is B cos omega ct plus theta naught. Now if you see the output x of t, which is we are getting from the multiplier, that will be as x of t AB sine omega ct plus theta I into cos of omega ct plus theta naught, which is on further operation will give us the AB upon 2 into sine theta I minus theta naught plus sine twice omega ct plus theta I plus theta naught. Now again in this particular equation, the last term which we may observe on the right hand side, so being a high frequency signal, it is suppressed by the loop filter, which is our H of S, which in a low pass narrowband filter. Therefore the E naught of t, which we are considering as an input to the VCO, that will be given by AB by 2 sine theta I, where theta I we may consider as an theta I minus theta naught, where this particular theta E angle, that's basically a phase error which we are considering over here. Now if you just check the next figure, which is here on the left hand side, which is the basically plot of E naught versus theta I. Now using this plot we can explain the tracking mechanism of the particular PLL. Now suppose that the loop is locked, means that the frequency of both input and the output sinusoids are identical. This means things are in a steady state, and therefore theta I, theta naught and theta E are the constant. Now this figure is a typical operating point A, so which we are observing, and the corresponding value of E naught and theta I. On this particular E naught and theta I plot. Now suppose further the input sinusoid frequency suddenly increases from omega c to the omega c plus k. This means the incoming signal, which is a cos omega c plus k into t plus theta I, will be represented in this particular form. As a cos omega ct plus theta I cap, where this theta I cap is the kt plus theta. Thus the increase in the incoming frequency that causes theta I to increase to theta I plus kt, therefore increasing this particular theta I. Now the operating point A, which is now going to shift upward along the E naught versus theta I. Now this increases E naught, which in turn increases the frequency of the VCO output to match the increase in the input frequency. The similar reasoning shows that if the input sinusoid frequency decreases, the PLL output frequency will also decreases correspondingly. Thus, the PLL tracks the input sinusoid. The two signals are said to be mutually phase coherent or in a phase lock. Therefore, the VCO tracks the frequency and the phase of incoming signal. The PLL can track the incoming frequency only over a finite range of frequency shift. Now this range is called the hold-in or lock range. Moreover, if initially the input and output frequencies are not close enough, the loop may not acquire lock. Therefore, the frequency range over which the input will cause the loop to lock is called pull-in or capture range. Also, if the input frequency changes too rapidly, the loop may not get locked. So as here in this particular discussion, though we are considering theta I and theta naught to be constant, the preceding analysis basically is also valid if these angles are varying slowly with time. Now it is clear that theta naught tends to follow the input angle theta I closely when PLL tracks the input signal. The difference theta E, which is nothing but the theta I minus theta naught is either a constant or a small number which may be equal to 0. If the input sinusoid is noisy, the PLL not only tracks the sinusoid but also cleans it. The PLL can also be used as an FM demodulator and frequency synthesizer. The frequency multipliers and dividers can also be built with the help of PLL. The PLL, being a relatively inexpensive integrated circuit, and has become one of the most frequently used in communication circuits. Now, in another applications of the PLL, consider with the space application, for example in the space vehicle, because of the Doppler shift and the oscillator drift, the frequency of received signal has lot of uncertainties. The Doppler shift of the carrier itself could be high, maybe in the range of plus minus 75 kilohertz. Whereas the desired modulated signal band may be just 10 Hertz. Now, to receive such a signal by conventional receiver would require a filter of bandwidth 150 kilohertz. When the desired signal has a bandwidth of only 10 Hz, so this would cause an undesirable increase in noise which may be received by the factor of 15,000. So because of the noise power is proportional to the bandwidth, therefore the PLL proves convenient, and hence because it tracks the received frequency continuously and the filter bandwidth required is only the 10 Hz. So though it is a non-linear system, the detailed analysis will help us to understand further how the FM demodulation that can be done with the help of this particular phase lock loop. And having this numerous application as well as the advantages, okay, so the PLL is going to be used in commercial circuits for FM demodulation. So I hope you understood what is the phase lock loop and what are its importance and how it is going to lock the loop, basically concerned with the input and the output sinusoid. The next video we will going to talk about how this particular PLL is going to use for the FM demodulation. If you have any query, so you can post it to our Google Classroom, and we can have the discussion over there. Thank you.